Welcome! So today's lecture is about abstraction and modularization, which are topics we've been touching on as we've gone through, but now we're going to draw together some discussion of those in one place. I should say, I think this lecture goes all the way through, so it's probably particularly important that you're prepared to pause when you need to pause and take breaks and what have you. So, like functions, classes can be used to break a problem into more trivial subproblems which can be tackled one at a time. So the art of deciding which functionality out of the total collection of functionality of your system and which data out of all the data that your system needs to manipulate should live where and in what collections is the heart of software design, which is a topic we can only touch on just now, but it is absolutely crucial both for maximising your chance of getting your system correct in the first place and for minimising the cost of changing your system as it inevitably happens that things change around it, whether that's the user's requirements changing or whether it's the technical environment changing. And of course it's not unique to software. We've got a pretty picture here of a car and a pretty picture of all the pieces of a car. And you can even look within one subpart of a car and split that into smaller pieces. And of course, all of these processes have analogues in software as well. Here is an early example of what we might now call a model, a description of how things are put together in parts and how they can be specialised into kinds of things. Again, this notation is not quite UML, it's one of the earlier pieces of notation that influenced UML. But it says things like a board game comprises a region and an empire, and a ship can be either a trade ship or a warship, and so on. And so this is basically taking a very complicated world of different concepts which are related in particular ways and starting to understand how they relate to one another. I think we introduced terms, possibly with slightly different definitions, a few lectures ago. I think these are consistent with what we said. So abstraction is the ability to ignore details of parts in order to focus attention on a higher level of a problem. And I think at an earlier stage I drew a distinction between abstraction and encapsulation. Encapsulation involving also the enforcement of non-dependency on details, and we'll come back to that later. Modularization is a bit more general. It's the general process of dividing a whole into parts, deciding what your interfaces should be, and so on. So we're going to play a bit with the idea of a clock display, and as always it's an artificial example, basically made as simple as can be in order to help you get the basic ideas, so don't get too hung up on how realistic it is or isn't, just let's focus on the ideas. So we're going to have some software supposedly to display a clock which has two numbers, one number for the hours and one number for the minutes, as shown here. We could think of it as being one 4-digit display, or we could modularize it and think about it as being two 2-digit displays. And there are some advantages of thinking of it as two 2-digit displays. For example, it might make it easier to avoid errors like having 1:103, which wouldn't be a sensible time. Again, we're going to use class diagrams and object diagrams, and again I'm going to twitch because these are almost but not quite UML. That doesn't really matter, there are lots of closely related notations. So, on the left we have a class diagram, and that shows the classes and the relationships between them. And so you can think about this as being a diagram that represents the source code level, so it's at what we might call a static view. There's a class car, which is going in Java to be recorded probably in a file car.java, and there's a class engine, which is probably going to eventually be implemented in a class engine.java, and they're related, that arrow shows, by the idea that the car is going to use the engine or contain an engine or in some way depend on an engine. The direction of the arrow usually indicates the direction of dependency. And when one thing depends on another, one of the ways to think about this is, if the thing at the head end of the arrow changes, it is possible that the thing at the tail end of the arrow may have to change as a result. So the way to think about this is, if the car changes, it's not the case that the engine itself will have to change as a result, but if the engine changes, the car might have to change in some way. Perhaps if the engine gets bigger, there might have to be more space left for the engine in the car, or whatever it is. But the engine doesn't know or care which car it's in, and so the car could change without the engine having to change. An object diagram, as on the right, is a runtime concept, the dynamic view, and it shows individual objects and relationships between them at some particular moment during execution. So the idea here is that we're showing a particular car, whose name is my car, and its particular engine, which is going to be labelled V8 petrol or whatever. So let's think a bit more about the class diagram situation. Here's a class diagram for our clock display. So here what we're going to say is that there's a clock display and it's going to use some class number display. In fact, it's going to use two number displays. Any individual clock display object is going to have two references, each to a number display object. And the first number display object is going to represent the hours, and so the number that it will display is 11 in our example situation at runtime. And the second number display is going to represent the minutes, and in our example situation that we had before, that was going to display 03. And here it is in Java. So what do we want to say? We want to say, okay, there's going to be a rather simple class number display which just has a limit, so that the idea there is that that's the highest number it can display, and a value which is going to represent the current value that it is displaying right now. And presumably it has to have a constructor, and it has to have some methods to do stuff like get the string representation of the current number and change the number as appropriate. Now the clock display is then going to use the number display, and the idea here is that it makes our task of deciding which functionality to put where simpler, because it means our clock display class does not have to implement methods for doing things like producing a string representation of a number, or providing methods for changing that number. It can just use that functionality from the number display class. So what we've got here is we've got two object references to objects of type number display, one for hours and one for minutes. And again, we're not going to talk about the constructor and methods just yet. So here's our API for the number display class, represented, this one actually is UML. We have a compartment at the top with the class name, we have a compartment for the instance values of the class. In this case we've got two integer values, limit and value, and they're both private. That's what the minus there means. They can only be accessed from inside this class's own code. And we should have a constructor of some kind. That should actually be called number display, not ctor. Ctor is short for constructor. And some methods. We're going to have get value, get display value, set value, and increment, just for the sake of argument. These are the messages that we've decided we expect to be able to send to an object of class number display. So for example, here is a constructor for the number display. It's going to take a rollover limit integer, which it's then going to store in the limit instance value of this class, and it's going to set the initial value to be 0. We talked about constructors last time. Remember that they have the same name as the class, they have no return type, and what they do is they initialize the state of the object instance. They can do other stuff as well if necessary, but that's their basic functionality that they normally do. Now we're going to take a short interlude, and we're going to discuss why it is that, as I think I've said several times already, instance variables really need to be private. Let's use a Dalek example, because this is slightly fun, okay? So here we have an unprotected Dalek class with public instance values. So we've got a public double battery charge, which is initialized to 5, and we've got a battery recharge method, which takes some double and does some stuff, presumably increases the value of battery charge, and we've got a move method, which takes a distance integer, and presumably, if we could see the functionality of that, it would not only move the Dalek, but also decrease the battery charge in some way. And of course we're missing some stuff. We haven't here got any representation of where the Dalek actually is, so how would it move? But you see the idea. You can take this as being a small subset of the possible code. Now here's what a client might do in this case with the public instance value. It might create a new Dalek object, and D then is an object reference to a new Dalek object, and then it might disable it by setting its battery charge to -infinity. And what happens there is that whether we or anybody else call the battery recharge method, presumably what this does is to add 1,000 to the current value of battery charge. Unfortunately, if you add any finite value to -infinity, it's still -infinity. Oh dear, the Dalek can no longer move. You could wonder about how it is that we get to create this Dalek that we then disable. Wouldn't it be easier to just not create it? But okay, suspend disbelief for a moment, please. If, on the other hand, we make the battery charge private, which is what we should do, and we try to do the same thing again, then we're going to get a compile time error because client code which is outside the Dalek.java class definition, is not allowed to access, let alone change, the value of a private attribute. Okay. So that's just a slightly fun illustration of the fundamental idea of encapsulation, which is to say you should keep the data representation hidden behind, in Java's case, private access modifiers. And so what you expose to clients of your class is not directly the data for them to modify however they will, but an API which may provide them with the ability indirectly to change the state of the object. For example, you can provide to clients a method which will have the effect of incrementing the battery charge, but the method that you provide for them to call to do it can do whatever checks it likes to check that it's being called in an appropriate way and that it only sets the actual battery charge to some sensible value. And that gives you a lot more safety and a lot more security about what can actually happen. It also has another advantage, which is the one on the slide here, which is to say that you can actually change internal representations without changing the client, because if the client couldn't access the data value inside, then actually it can't possibly depend on exactly what the type or the representation of that state is. So in an encapsulated data type, instead of allowing clients to touch the data to do what they want, clients have to ask the object to manipulate its data, and the object will be the final arbiter of whether or not it does that and exactly what it does. Notice that a fundamental aspect of the object-oriented way of programming is in fact that the behaviour of the object is also in a sense encapsulated. So when you send a method to an object, when you send a message to an object, you're not directly invoking a function. The reason we talk about sending a message is because it's ultimately up to the object what code it executes in response to that message. And when we talk about inheritance later on, you'll see more about how that works. So, we've seen access modifiers public and private, and on this slide we're going to talk about also the default modifier, which is what happens if you write an instance variable and you don't put either public or private in front of it, and that's the default modifier. So the point about this table is where can code live that is going to actually access the modified attribute or what have you. So if the attribute is labelled public, then the answer to that is literally anywhere. So code could be inside this class, it could be in a different class inside the same package, or it could be somewhere else entirely, globals, in a completely different package. Any code anywhere can access a public member of an object. Okay. For private, as I said a moment ago, only code that's inside this very class can access it. Okay. Now the default modifier, if you miss out either private or public, has the slightly bizarre property that code which is inside the same package can access it, but code that's outside the same package cannot. However, don't use that. These days it is considered to be bad style within Java. So just use public, private, or when we meet them later, protected, as may be appropriate in your particular case. Yes, the fourth modifier is the one I just mentioned, protected. You're going to get to know that later. Right, so on to the number display's instance members. So now we're going to give our number display a private integer limit and a private integer value, and they're going to be initialized inside the constructor. Now, the object state does get default values, so if we didn't initialize them inside the constructor, they would both get values 0. But it's quite convenient to put the initialization explicitly in the constructor in any case as documentation of what we intend. Since the rollover limit presumably should not change in the lifetime of an individual object, it's quite useful to use the final modifier to indicate that, so that if we accidentally write some code later on that changes the limit, the compiler will warn us that we probably didn't want to do that. Okay, so in an immutable data type, the object's internal state cannot change after it's been constructed, and we saw that last time when we looked at the string API. It's also the case, of course, for any of the private types, the primitive types, because they're not objects at all. However, we've seen lots of objects in Java which have the kind of default setting, which is to say that the internal state is mutable, it can be changed, and Dalek is one. We saw its battery charge can be changed, and you've seen how to change arrays, and so on and so forth. Immutability has advantages and disadvantages. Coming from a functional programming background with some experience in Haskell, you may find yourselves quite sympathetic to the idea of immutable data, because that's fundamentally what you have in Haskell. Sometimes in Haskell you'll hear the phrase referential transparency. I'm not sure if you found out last semester what that means. You can look it up if you're interested, and if you didn't. The property of data that it is immutable sometimes makes programs easier to debug, partly because it limits the scope of the code that can change values that you're interested in. It makes it much easier to write concurrent programs, and in Java that's the major reason why immutability might be a style that you would like to adopt in a particular system. And it allows you to pass objects around without worrying about modification, of course, because they can't be modified. The disadvantage is, well, sometimes the resulting code can be less clear, and you can find that you're losing some of the advantages of object orientation, throwing the baby out with the bathwater, as it were. In particular, if you can't obviously if you can't change the data after an object has been created, then any time you want an object that contains a new value for some element of its data, you have to have a completely new object, and that can just get a bit confusing. So watch out for this issue, and when you're reading documentation, notice if it's going to tell you that data is immutable. The final modifier did come up previously in some lecture, and you've seen it already. What it means is that the value doesn't change after the object is constructed, and it helps enforce immutability and prevent accidental changes. I said this. And so sometimes that kind of thing can make the program easier to debug. In general, any time something ought to be true about your system, it is helpful if the compiler can help you to verify that it really does stay true, because humans make mistakes, including people who come along and modify the code. And this is, for example, it's one of the reasons why we even like to have a type system in our programming language. It's why you may find it annoying if the Java compiler tells you your code doesn't compile because something has the wrong type, but that's very often helpful because it helps you to catch an error at compile time that otherwise you wouldn't find until runtime. If you've programmed in languages like Python, for example, that don't have a static type system, you may be starting to have some feel for the advantages and disadvantages of that particular aspect of having the compiler help you to catch your own errors. There are always kind of horses for courses and pros and cons to all of these things, which is why language design is an interesting challenge and why software design is an interesting challenge. We're only really scratching the surface here, of course. Right. Sometimes we do want a way of accessing the object state, and you might say, oh, well, maybe this is an argument for making the data attributes public in this particular case, but usually it's a better idea to provide a getter method like this. So here we've got a getValue method, which is doing nothing more nor less than returning the current the current state of the value. But notice that because it returns it, it's telling a client what that value is, but it is not in itself allowing the client to change that value. And moreover, if we, for some reason, wanted to change the representation of the value to, I don't know, being a double or something, but we still wanted to return an integer to clients, we could perfectly easily do that. We could just somehow turn our double into the nearest integer or something and return the integer. And the clients would be able to retain their ignorance of the data representation, and that would be a good thing. So sometimes you can have a more sophisticated access. So this one is not literally returning the value of any data attribute. It is actually constructing a value to return from the value of a data attribute. And so it can do some checking or whatever, some reformatting, whatever it might be. Note the conversion trick for string and number. Oh, yuck. Yes, okay, fine. It's converting a number into a string by adding the empty string to it. That's a bit yucky, but there you go. It works. Sometimes you also want to change the state of an object, but you'd quite like to have some kind of checking to make sure that instead of just allowing a client to set, in this case, the value attribute to whatever it would like to set it to, it's actually the method is now going to enforce some kind of limitation on what changes the client is allowed to make. So in this case, the method here is checking. It's not just taking the replacement value that's provided as an argument to it and taking that to be the new value for its value data attribute. Instead, what it's going to do is, first of all, it's going to check that replacement value is positive and less than the allowable limit, and only if both of those two things are true, it's going to take that replacement value as the new value for its data attribute. So this is giving us a bit of extra safety. Of course, this is only interesting for mutable objects. You can't have any setters in immutable objects. And here's a more sophisticated mutator that is going to do some computation on the value. Yeah, some people might not even call this a mutator. It is a method that mutates a value, I suppose, so yes, it counts as a mutator in that sense. We are incrementing the value, we're adding 1 to it, and then we are taking the value mod the limit, in other words, so that we don't accidentally go over the limit. If we've reached the limit, we're going to go back down to 0. So, getters and setters, instance variables should be private. Have I banged this home enough yet? I guess I have. Here's a student class with its private data values, which are initialized in the constructor in the way that should be becoming familiar. And here is a client of the student class. It's going to create a new student. It can attempt to print out the data value of a particular student, but it can't do it because they're private. It's not allowed. So, to summarise, in order to be making full use of the encapsulation capabilities of object-oriented programming, in Java in particular, your instance variable should always be private, and we use methods to mediate whatever access to the data we wish to provide. We might provide some accessor methods which just read the data, or indeed which read the data after doing some checking or some reformatting. We might provide some mutator methods that actually modify the data, again, plus or minus doing some modifications or some checks to the request that it's finding. So a Java convention is to write getters and setters. So the naming conventions would be that if you're going to have a method to read an instance variable myData, it's going to be called getMyData, and if you're going to have one called to set it, then it's going to be called setMyData. And in fact, if you're using an IDE, then very likely your IDE will provide you with the ability to automatically write the code for those methods, saving you several seconds worth of typing. And these things are often called getters and setters. Right, so here are some getters for the student class that we saw a moment ago, and these are going to be the totally simplest possible versions. They're just literally going to return the appropriate strings. Right, back to our number display API. Here is the latest version of our number display class. We've got our constructor, and we've got a getter, a simple getter, and a slightly more complicated getter that's going to get the display value, and we've got a setter with its check, and we've got an incrementer. This is just the code you've all seen before, but all on one slide this time. And here is an extended object diagram for this. So now we've got a clock display class, and it contains two object references to two different number display classes, and we can see now that number display classes each have their own limit and value in them. So hours, there are 24 of them, so that's the limit, and minutes, there are 60 of them, and that's the limit, and so it goes on. Same code will control both the hours number display and the minutes number display, because we carefully designed it with this limit field, which could have different values, but the actual behavior we want, which is to say that it ticks over to the next to 0 again when it goes past the limit, is the same in both cases, so that's convenient. We have a clock display API, a bit like this, and just for the sake of argument we're going to say that we have a time tick method and a set time and a get time on there. We're going to say we have a private method update display there, and we're going to have two constructors here. I don't actually know why in these diagrams the constructors are being labelled with CTOR. It would be much more common in UML diagram to actually put what you would expect to see in the Java code, namely clock display, the actual name of the class there, rather than CTOR. Okay. So, accessors. So the get time is going to return the display string, which has got to be a data attribute of an instance variable of the class. I keep saying, by the way, data attribute, instance variable. These terms are synonymous, so that's why I keep saying one or the other, or saying both. We can set the time to a given hour and minute, and we're going to call an update display method after we've done so to make sure that the new time gets properly displayed. And we can tick the timer, in which case we're going to use our increment method that we previously wrote in the number display class. I think that behavior is pretty clear. Notice we've got a private update display method, so this is a message which can only be sent to an object of this class by an object of this class. So typically an object sends itself the message update display, exactly as you see here in set time and timer tick. And what this update display method is going to do is to reset the value of display string to the thing that's supposed to be the current value of it. Now let's look at the constructors. We've got two constructors, and you briefly saw the possibility of having two constructors in the previous lecture, I think, where we had a circle that could either have its radius set or not have its radius set, in which case it got a default radius. So in this case, a very similar thing is going to go on. We have a 0 argument clock display constructor, which is going to set us to some default value. And we have a clock display constructor which is going to take an hour and minute value to be the initial values of the time, in which case we're also going to call that set time method with the hour or minute. And it had better be the case that set time itself calls update display, otherwise we're going to be in a situation where one of these constructors calls update display and the other doesn't. That's the kind of thing you might expect to have to check. This is called overloading the constructor, because we've got two constructors for the same class. You can think of it as being two sort of methods with the same name, in this case clock display, although recall constructors are not really literally methods. You can overload other methods, not just constructors. So what we mean by overloading is that we have two methods with the same name, but they have different parameter lists. So, for example, you might have two add methods, one of which adds two integers and the other of which adds two float values, and we trust the compiler to work out which of these two potentially unrelated methods is to be called in each particular case, depending on the arguments that are being given to the method in each particular case. You've already seen this, in fact, with println. You're used to the idea that you can print all kinds of different things using the same method, system out println. You can print strings, ints, doubles, and what have you. This is called method overloading. So in summary, Abstraction is the ability to ignore details of parts of the system in order to focus attention on a higher level of a problem, and modularization is the process of dividing a whole into well-defined parts which can be built and examined separately and which interact in well-defined ways. The summary of access control: all instance variables and methods are visible within the body of a class. Whether you want any more access than that is a design question for you. By strong convention within Java, instance variables should be private, meaning that members are only accessible within the class. Methods might be either private or public, depending on whether you want them to be available for every client to use or whether you want to keep them for use only within the class. The more you encapsulate, so the less access you provide to clients of your code, the looser your coupling. That is to say, the narrower the dependencies are of clients on your code, because clients cannot depend on something they can't even use. And that makes it easier to make changes to your code in future, because it gives you more scope for changing your class in the confident knowledge that you cannot be breaking any client, because it's impossible for some client to be depending on the thing you're changing. Having carefully designed an API of methods that should be available to the outside world, you export that and document it and commit to supporting the API. That's the idea. Okay, and that's the reading for this lecture.